Test, test. Okay. Hello, everybody. Hopefully my voice holds out here. I'm Dr. Maloney. I'm the physics professor here at Dakota State University. I wanted to kick things off today. Welcome, everybody, to Space Day 2018 here at Dakota State. Hopefully we're going to have a really, well, not hopefully, we will have a really great program here for you today. Lots of interesting things that we've got going on throughout the morning and early into the afternoon here. I'm going to kick it off with a short introduction from our president, who's here to give some introductory remarks. Dr. José-Marie Griffiths is president of Dakota State University. President Griffiths has spent most of her career in research, teaching, public service, corporate leadership, economic development, and higher education administration. She's been awarded presidential appointments to many national boards and has led projects for over 28 U.S. federal agencies, including NASA, and for over 20 major corporations and 7 major international organizations. She's received many significant awards in science, technology, teaching, and the advancement of women in these fields. She's been president of Dakota State University since 2015. And without further ado, President Griffiths.
Thank you very much. What you really should have said is, here's the other physicist in the room. No, the second one. So I wanted to welcome you all here today to DSU Space Day, and soon we're also going to be welcomed to the International Space Station. Before we link up to the space station, I'd like you to think about how progress has always required us to think differently about things. As we sit here, the space station is rotating around Earth. It's about 240 miles above the Earth. Many of you, I'm sure, have been to Minneapolis or have been to Omaha or Lincoln. Well, it's further to the space station. It's about 7/8 of the way from Madison to Rapid City. It's about the distance to the Minuteman missile, if you've ever been there on your way out to Rapid City. And it takes somewhere, depending on how fast you drive, between 3 and 4.5 hours, and depending on the roads that you have in between there and here that you're taking. But in your great-grandparents' day, the time that this university was founded, it would have taken about 7 days to travel that distance, and that's if they had a good horse. So a good horse could travel about 35 miles a day. Today, when we talk to the astronauts on the space station, our communication will travel that distance in milliseconds. And between those two situations, some smart people dared to think differently and challenge the ways we've moved across the miles. In a little over 100 years, we've reduced from 7 days to milliseconds to travel that distance and to talk to someone at least 240 miles away from us. Another comparison I'd like you to think about is the advances in technology that have made today's downlink with the space station possible. You're sitting, as you know, in the Beacom Institute of Technology, which is filled with leading-edge computers and software and networking, technology your great-grandparents couldn't even have imagined. But let's bring it down to something more personal. Raise your hand if you have a smartphone. It's a silly question these days, isn't it? But you know that the Apollo 11 spacecraft, the 1969 first manned mission to land on the moon, that spacecraft had less computer power in it than your smartphone. You could download to your phone all the software that was used to control the Apollo 11 mission, open and run the apps, and still have room and operating cycles to text your friends and listen to your favorite tunes while carrying out your mission on the moon, likely simultaneously filling your feeds on Snapchat, Twitter, Instagram, or whatever social media app you favor. Between those two situations, the Apollo 11 mission and your smartphone, some people dared to think differently, and now you have a pocket full of powerful technology available to you 24 hours a day, 7 days a week. And I'd like you to think about one other comparison, that of gravity versus weightlessness. Look around you and think what would happen if we could throw a switch and turn off gravity's force here in the Beacom building, or propel this building and everyone and everything in it 240 miles up into space and to weightlessness. What would happen? Well, we'd all start floating around this room, along with everything around us. How would you get across the room? What would happen if you have stuff with you? Backpack or a water bottle or a sweatshirt? If you ended upside down, how would you get yourself right side up? How would you keep yourself from being flattened against those windows or stuck underneath the floating conference room? How would you get out of the way of all the floating chairs and couches and tables and watermelons and everything else that's around here? And what if I suddenly announced that you needed to leave the building? How would you get out? How would you even open the doors? 300 years before space travel, Newton figured out the science that the further away an object moves from a mass, the less gravitational force is felt. But it wasn't until space travel that people actually had to figure out how to manage activities in a weightless environment. Between Newton and the space station, a lot of people had to think very differently about how we do things, from brushing our teeth to walking across a room in a weightless environment as opposed to one with gravity. All progress occurs because someone dared to be different. And today I want to challenge you to be different. You might come back to me and say, I don't want to be different, I want to fit in. But to fit in at every level of your life, to be who you're meant to be, each level will challenge you to be a different you. Do you know there were 2 astronauts who were born in South Dakota? If you're from South Dakota, have you ever thought about whether you might be the 3rd? Think differently about yourself and try on that idea. What's going to be the next technological game changer after the smartphone? Who's going to develop that technology? Might it be you? Who's going to find the cure for cancer? Is that you? Who's going to be the next teacher to educate and inspire generations of students to do phenomenal things? Will that be you? Who's going to be the person to develop computer systems in the US that are truly secure, fully protected from those who want to do us harm? Are you going to be the one to think differently and come up with better ideas and make progress for all of us? We're going to be able to talk today with astronaut Richard R. Arnold II. Astronaut Arnold is someone who it appears had to think differently about himself at different times in his life. After he graduated from college, he was a middle and high school mathematics and science teacher for 16 years before becoming an astronaut in May 2004. You might want to ask him how he went from being a middle school teacher to an astronaut. That's certainly a path different from the one I would usually think of for someone to become an astronaut. At some point, he was like all of you students and teachers who sat in meetings like this, just like everyone else. However, something changed, and he moved to being one of the approximately 18,000 individuals who apply to NASA each year to become an astronaut. And he was chosen to be the one of about 18 people selected per year. Hearing those odds, only 18 out of 18,000 get the job in a year, can be intimidating. And I'm sure some people see those odds and never even fill out the application. However, thinking differently about yourself can have you walking through doors you could not previously have imagined being open to you. So progress has always required people to think about things differently, even to thinking about themselves differently. Those of you here today who are students, either high school or DSU, I challenge each of you to think about things differently, including yourselves. As we participate in this downlink today, I want you to think higher and wider than you ever have before. I want you to think about whether some years from now, you might be the one talking to the rest of us from the International Space Station, or be the mover or shaker in whichever field excites you and fires your passion to be different and to make progress. I'll leave you with a quote from Ralph Waldo Emerson as a challenge today. Do not follow where the path may lead. Go instead where there is no path and leave a trail. Thank you very much. Enjoy the day.
We have a couple other words of welcome here from some special guests who couldn't be with us today but wanted to say a few words. First, I'd like to introduce Governor Dennis Daugaard. Dennis Daugaard is the 32nd governor of South Dakota. Governor Daugaard has emphasized job creation, sound fiscal management, and efficient government operation. He's prioritized sound stewardship of our state's resources, and under his leadership, South Dakota was named the best-run state in America and obtained the highest bond rating of AAA from all 3 rating agencies. So we have a short welcome from Governor Daugaard.
Hi, I'm Governor Dennis Daugaard, and I want to welcome you to Dakota State University for Space Day 2018. Though I can't be with you, I know Space Day is a great opportunity to learn about science, technology, engineering, and math, or STEM, from DSU professors, scientists across the nation, and even an astronaut on the International Space Station. DSU is a fitting host for this event because the university is a leading STEM institution with over 2/3 of its students enrolled in a STEM major. STEM fields can be a great career choice with growing job opportunities and good wages. The U.S. Bureau of Labor and Statistics reports above average growth in STEM occupations from computer-related jobs to astronomers to teachers. Now, while many of these jobs require college degrees, some, such as web developers and engineering technicians, just require an associate's degree. Students, I know you're going to learn a lot today, and I hope you will leave inspired to consider a STEM career for your future. Teachers, I hope you will take some of the concepts presented today and incorporate them into your classroom curriculum. As John Glenn put it, the most important thing we can do is inspire young minds and to advance the kind of science, math, and technology education that will help youngsters take us to the next phase of space travel. Enjoy Space Day.
Next, we have short introductions also from both our state senators who are busy in Washington this week. Senator Mike Rounds was first elected in 2014. Senator Mike Rounds is a junior senator from South Dakota. He serves on 5 committees: Senate Armed Services, Banking, Housing and Public Affairs, Environmental and Public Works, Small Business and Veteran Administration. He's previously served as the 31st governor of South Dakota for 2 terms and for 5 terms in the South Dakota State Senate, including as Senate Majority Leader. Additionally, Senator John Thune serves on the Agriculture, Nutrition, and Forestry Committee, the Commerce, Science, Transportation Committee, the Finance Committee. He's also chairman of the Commerce, Science, and Transportation Committee. Senator Thune also serves as the chairman of the Senate Republican Conference, the number 3 position in Senate Republican leadership. So I'd like to present a short welcome from both Senators Rounds and Thune.
Hi, I'm Mike Rounds. Welcome to Space Day 2018. I wish I could be there with you in person as you speak with an astronaut on board the International Space Station. What a great opportunity. I'm sure you have some good questions planned to ask him about his experience in space. Perhaps some of you will even want to become an astronaut after today. But even if that's not your preferred career path, a background in science, technology, engineering, and mathematics, or STEM, will help you navigate the job market in the future if you feel a calling to study these important issues. STEM-based jobs will continue to be in high demand for many years to come. As I'm sure you know, astronauts on board the International Space Station carry out different experiments and research to learn more about Earth and other planets in our galaxy. Many of you may know that I have a strong interest in these science-related activities, including the experiments that are taking place at the Sanford Underground Research Laboratory in Lead. The scientists there are studying neutrinos, dark matter, and the particles that we believe make up our universe. Their discoveries, paired with research from astronauts on the International Space Station, could answer age-old questions about how our universe was formed. It may sound like science fiction, but this is actual research being done in South Dakota, in space, and around the world right now. I'm pleased to see you take an interest in this important research and in scientific advancements. Thanks for the opportunity to talk to you today. Enjoy Space Day. Thank you.
Hello and welcome to Space Day 2018 at Dakota State University. I'm Senator John Thune. I apologize that I'm unable to be there today in person, but I appreciate the opportunity to address you through this video message. Today you will have the chance to talk to astronauts aboard the International Space Station, hundreds of miles above the Earth's surface, where Americans have been living and working longer than many of you have been alive. NASA's space exploration program has changed dramatically in that time, with new and exciting commercial companies like SpaceX and Bigelow Aerospace now providing many of the same capabilities that the government used to do. Aboard the space station, our astronauts are learning about the technologies and techniques it will take to get humans to Mars. As students, you are in a unique position to study the science and engineering that this journey will require, and you will graduate in a time that gives you more options than ever before to use them. Whether you work for one of the new space companies, a startup that hasn't even been founded yet, or for NASA itself. Today, though, your mission is simple. Have fun and enjoy Space Day 2018. Thanks again for this opportunity, and have a great day.
So we have a fairly packed program for everybody here this morning. We're going to start off with one of my cohorts over at the College of Arts and Sciences, Dr. Dale Droge, who's been here at Dakota State since 1992. So many of you know him, have taken biology with him, or some other course throughout the years. He's got a great presentation that I think will kick off some of the things you want to think about going into our downlink later this morning. So without further ado, Dr. Droge.
Okay, does that work? Yeah. I want to use the wireless mic here so I can move around a little bit more. Thank you. Welcome to Space Day. It's great. It's going to be a great opportunity here, I think, to do a whole lot of things. First of all, just, what Dr. Griffiths talked about and the others, I think humans have always had a great fascination with what's going on above us as they looked at the stars and the moving planets and the moon and things. There's always been an interest. And, of course, that just keeps getting more and more over time, and for a long time we had to be satisfied with observations from Earth through telescopes, even later on very sophisticated radio telescopes and things. But there's still been a desire to get there ourselves. It isn't enough just to know these things. We wanted to actually experience and send the explorer type mentality to get into space. And of course, with the rocket launches of the Mercury and later Apollo. And finally, we were able, what was almost a culmination of this was the moon landing that Dr. Griffiths mentioned in 1969. But since then, of course, we've been doing even more space exploration. The Mars rover, deep space probes. We now have, the technology has allowed us to go out and still gather more and more information. But it has not changed that desire to live and travel in space. Certainly much of our culture, science fiction, and other things, dreams and expresses that interest in that type of thing. So here we have, today we'll be talking to the astronaut on the International Space Station, which is an attempt, or, to exploring the possibilities of long-term survival in space. Okay. So what I want to talk about today, though, is there's more than machines involved. Okay, when you go outside the deep space probes, the Mars rovers, and those kinds of things, now you have to deal with another problem. You have to deal with the capabilities of the human body to withstand space travel and the kinds of things that, perhaps things that we don't have any idea might be happening out there. So this slide is from NASA. This is part of their biological program. They're interested, as you can see, in all types of things, model organisms. They're interested in, certainly human health, and then even exploration and these kinds of things, regenerative systems. If we're going to go through long space travel, we'll have to have regenerative atmospheres and food sources and those type of things. So there's been lots of research been going on, particularly on the space station itself. Okay, I want to talk. I'm just going to highlight a couple of things that that's been going on at NASA. I should probably throw in a caveat here. I'm not a space biologist. That's not something I typically study, but I was able to look at this and hopefully bring a little bit of lens of interpretation of what I know about biology. And one of the really interesting areas that a lot of research has been going on is in plant biology. And clearly, as I just mentioned, if you're going to have long-term existence in space, or if you're going to go certainly outside of Earth's orbit, interplanetary type travel, the ability to provide the food and other kinds of things that you need for that trip is going to become prohibitive. You can't just store all of that. It's going to be too much weight and spoilage and all these other kinds of things. So if we're going to do that, we probably are going to need some type of system of growing our own food as we travel in space. And of course, that's going to create a lot of problems to solve. So growing plants, we'll talk a little bit about, they've been doing a lot of research, growing plants in microgravity, that is, very, very small amounts of gravity that are present outside of, or at a distance from Earth. And this is known as the NASA Project Veggie, not terribly imaginative, but there you go. The things are, and so what do plants require to grow? They need light, they need nutrients, they need water. Okay, carbon monoxide, these things are. So those are the kinds of things they need. And you think, well, that's a big deal, but it's hard to do all that in space. So what they've come up with are these pillows, and you can see kind of up here in the upper left, they've flown up in a diagram. This provides the support that you need for a plant for gravitation. And then you can see inside of that pillow is the nutrients, the soil with fertilizers, and those or the types of nutrients that it needs. So it provides the substrate and the anchoring and the nutrients that the plant needs to grow. Now, one of the big problems, though, originally that people realized right away was when you're growing plants without gravity, you're going to put them in a situation for which they have not evolved. Plants evolved over millions and millions of years on this planet, obviously, with gravity. And clearly, back Charles Darwin and others noted that plants respond to gravity in their growth. This is called geotropism. It's growth in response to gravity. And you can see that basically if you turn a plant on its side, that over time the stem will grow up away from gravity, the roots will grow down toward gravity. And you can see the corn seeds over here on the lower right. You can see that what happens is even if you turn the roots away from gravity, over time they'll hook around and start growing down. So plants grow in response to gravity. And so we knew as you go to space, you think, well, this is going to be a problem. How are we going to direct the growth of the plants? Well, around 2010, they ran these experiments on the space station, and they came up with a big surprise. They found out that gravity was not essential to direct plant growth. Okay, this would not, one of these things where science comes along and by doing the experiment, you find out things that are pretty counterintuitive. So basically you can see here what we've got is on the right are the plants growing on the space station. On the left are the plants, planted at exactly the same time. They're control growing at NASA headquarters in Texas. And you can see what happened is, they're not exactly the same, but they're both growing downward. The stems are growing up, and the roots are growing down. Now they're held in a substrate, like an auger kind of situation. And so what they discovered was that these plant genes were expressing themselves differently in space. They were basically responding to an alternate cue, and that cue in this case was light. So the stems were growing toward light, the roots were actually growing away from it. So there's sort of a secondary mechanism, something totally unexpected. So in a way, that was a nice surprise too, because it took away one of the problems now with growing plants in space. And so now what they do is what they're working on. Space stations now have been working with these experiments quite frequently. They have these chambers. You can see it's kind of collapsed chamber. So inside that chamber are those pillows. You have the plant. You have LED lights. The astronauts over there are showing once they turn on the LED lights, that activates things. And they're providing, you can see the kind of the reddish light that's good for plant growth. And they don't have to, so the plant stems then directed upwards and the roots directed downward. And so that's been an important achievement. And in 2000, here's Scott Kelly on the right. Actually, we'll be talking about him again in a minute, our famous astronauts. And they were eating the first lettuce grown in space, grown totally in space from seeds. So they will eat this. They're pretending that it tastes good. And, but it worked anyway. And then since then, they've also been able to grow some zinnias, and you think, well, geez, flowers. But one of your big problems, a lot of things that you want to eat are fruits, right? Vegetables and things like that. Fruits are the result of flowers being pollinated and the growth. So in order to grow fruits like tomatoes and corn and things like that, not corn, sorry, flower, tomatoes and many of the vegetables, you're going to have flowering in space. And so to get plants to trigger, the flower to trigger and all that. And so they've been working on that. You can see growing in the pillows, and they have been able to do this. So there's some real promising achievements on this front and findings on this front. Okay, let's turn from plants now. All the power of the Apollo 11 module, and I'm going to use it as a clock. There we go. Okay. So, audience participation time. What were the first animals ever sent into space? Close. Actually, it's always the, whoops, got to point at thing. Actually, turns out that they were launched, this is, we don't think this is orbit, so that probably might be tricky, but the first organisms sent into space were fruit flies that were on a V-2 rocket launched in New Mexico in 1947 to a height of 68 miles. So they didn't go orbital, went up. They, rocket malfunction, they didn't survive. Okay, so these things are. Yeah, well, we tend to think of more than that. Then they started sending mammals and things into space, particularly what was the first mammal to complete an orbit? In this case, it was a dog. It was Laika, a dog launched into orbit in Russia in 1952. Laika also did not make it back. They weren't, in fact, there wasn't even a recovery mission in that case. They were monitoring physiological data as it went along. Okay, so I didn't want to be the main thing, but we have spent, early on in space exploration, before deciding whether humans would be able, or before sending humans up, trying to determine some of the potential problems and things, there were a lot of animals sent up. Little rhesus monkey up there in the right corner, upper right corner with its little spacesuit on. It's kind of trapped in there. And then this Ham is a famous chimpanzee right before the Mercury, one of the last ones launched, and he was recovered. Actually lived out to a ripe old age, and so he was an important contributor. And then I put down the bottom there, there's also ant colonies. The ant colonies were sent up fairly recently on the space shuttle as a student project, and one of these student projects that were suggested, how do ants communicate with each other in weightlessness and these kinds of things. So we've spent actually a lot of different animals into space to pave the way for humans. I had to throw this in because I love these creatures. These are the animal, maybe the champion space animal, are a very little known group of animals called tardigrades, which are microscopic. You can see very strange looking little creatures. And things are, they actually can survive without water, desiccated for months and months and months. We knew this on Earth. We also looks like now that they may even be able to survive, not only on a space station could they survive, they may be able to survive outside of, in the vacuum of space for considerable periods of time, and then regenerate. So it's just, they're pretty interesting creatures. Okay, I like animals, so we have to talk about it. Okay, first human to go into space. And things are, you probably know he was a Russian cosmonaut, Yuri Gagarin, in April 12th, 1961. So first started much of the Sputnik, era space race, things are. Just about a month later, Alan Shepard became the first American in space. Probably a few of us in this room sat in our grade school classrooms watching these grainy photographs of the space launch, and his very short, he didn't do a complete orbit even, but he's the first American to achieve that type of status. With a year later, John Glenn orbited the Earth. So very rapidly, a lot of progressions in humans. But that leads then, so the things are, we went to the moon, took weeks, these kinds of things, but we're still the next chapters in space exploration. If we're going to go interplanetary, if we're going to establish, bases on the moon or Mars or other types of things, this involves biological limitations, perhaps. What is the human body's reaction going to be to long-term exposure to space? So right now, what's the longest time anyone has ever spent in space? It is C, 438 days. Valery Pelikov back on the Mir space station before its demise. So really, just a little over a year is the longest time that anyone has ever spent in space. And it will take at least 2 years to get to Mars by current technological innovation. So we don't know a lot about what's going to happen. So a lot of study, NASA spending time going through and looking at what are the, how does living in space affect the human body? And I'm not going to try to do an exhaustive review here, but talk about a couple of things that we know. And of course, you've got, when you're in a space situation, you've got microgravity or very low gravity at all. You've got influences, kinds of things that you can eat and how that's going to affect your body. Limited activity, which might affect muscle atrophy. Also, the microgravity feeds back on this. And of course, just the stress of being in such, tight quarters and under those kinds of isolated circumstances. Okay, one of the weird things that goes on, microgravity affects body fluid. You can see in the diagram on the top that on on the ground things are, but in the initial stage of space, the microgravity, the fluid starts to move up and towards your body. You can see Dr. Mackay there, how much edema, the swelling, the fluid that's flowing up to her face after initial things are. So it does calm down a little bit, as you can see, when you're in there for a little while, or you're in those microgravity situations for a while, the body tends to, proteins, different kinds of mechanisms kick in and regulate that, but it's still distributed differently than it is on Earth. So you're going to have body fluid distribution issues that you're going to have to deal with. Bone density is a big problem. You know, we know that lack of activity, right? If someone's on Earth, even if you're in gravity, if you're not moving around a lot, or you're not, you know, if gravity's not pushing on your bones, or you don't have that kind of stress on your bones, that bones will, as living tissue, they will scavenge that calcium and take it off to do other kinds of things. And this happens a lot in space. So with the lack of gravity, you can get a great deal of bone density loss. You can see the diagram on the right would be what's happening low mineral density as that type of, as that sponginess increases and the calcium is taken away from the bones. So one of the things they do on space stations and other places, they have fairly vigorous exercise schedules. They do weightlifting, they do a lot of training. They exercise a lot, trying to prevent the muscle atrophy, trying to limit the bone density. Because some of these bone density incidences are pretty hard to recover from. Some of that inner bone density loss, they found that does not recover even after the astronauts have returned to Earth. So in a way, it weakens bones. You may have seen this, I didn't have a picture here, but you can say a lot of times when an astronaut gets back from a long period of time, they can't walk on land. You know, they have to be supported. You know, it takes a while to adapt to full gravity, full Earth gravity. Okay, that leads kind of things are to kind of talk one thing about some really interesting things happened. A very recent space flight. You may remember this one. It was in the news quite a bit. We had these two twin astronauts, identical twins, right? They were, you know, monozygotic twins, genetically very, very, very similar. Scott and Mark Kelly. Scott on the right, Mark on the left. He had a mustache for a while just to help people out a little bit, I think things are. Also, Mark Kelly's married to Gabby Giffords, the senator, or the congresswoman from Arizona. So he was in the news a lot for that. Anyway, so these two were getting started. And they, you know, NASA saw an opportunity here for a fairly useful scientific study, that you have two individuals who are genetically very similar, have been raised in similar environments and those sorts of things, and they're astronauts. And Mark had retired, so he was going to stay on Earth, and Scott Kelly was going to go to the space station, and then they would track just thousands of variables and different kinds of things to see what kinds of differences they could determine. Okay, it's not a perfect experiment, but it's a pretty good control group. It's better than you could normally come up with. So Scott Kelly lived on the International Space Station a little less than what they had planned. I think he was supposed to be there about 380 days, ended up being 340 days, so almost a year. That actually set the record for American endurance. He has the longest amount in space, in one trip. He actually, I think he might have the world record for the number of cumulative days in space. I can't quite remember. Pretty close at any rate. Anyway, so he was in there 340 days, and we'll just look at a couple of the things that happened. First of all, he came back, one of the kind of interesting things, he was 2 inches taller than his twin, okay? Gravity, you know, compresses us down. Without gravity, you know, his bones, you know, space is starting to fill and things. That didn't last very long, okay? That was a you know, the NBA is not going to be interested in this kind of result. They're not, you know, it comes back. Some interesting things. Mentally, they gave them a lot of cognitive tests, different kinds of activities, response times, figuring out things like that. As long as when Scott was in space, their results were very, very similar and matched baseline kinds of things. But actually, when Scott returned to Earth, then he reported having some problems with some of the cognitive. You know, he was kind of a little foggy, as he called it, in some of these things. It returned to normal eventually, but there was an initial kind of reduction in cognitive abilities upon return. And just some kind of weird things happened. His arterial walls thickened. Nobody knows exactly, and they don't know if they're going to go back to normal. Things are, but these are the kinds of things they were measuring. and looking to see at these the kinds of differences. Interestingly, they're microbiomes. This gets a lot of attention now in diets. Microbiomes are the bacteria and other kinds of organisms that live inside your gut. They have a lot to do with how you digest things. They differ anyway. I mean, no one's microbiome is probably going to be exactly the same, but his changed a lot from when he was on Earth to when he was in space. And nobody knows exactly, again, what that all means for sure, except probably the environment, the environment he was under, the stress he was under, and the diet he was under probably changed that. These are some of the things that got reported more in the news. There were some interesting changes in genes themselves. One of them was telomeres lengthened. Telomeres are these caps that are on the end of chromosomes. Longer telomeres are generally associated with longer life and things like that, less mutations and things. So they did lengthen, and that's a real interesting result. Nobody knows exactly what that means either, but this is an interesting result. And they did shorten again once he returned to Earth. So those type of looks. And these are the ones, again, King's Road. There also were some mutations and other types of things going on. There's always mutations, and we'll talk a little bit more about it in a minute, but all of us are undergoing mutations all the time. We've got millions and millions of base pairs of DNA being copied constantly. Mistakes happen, okay, and environmental things affect it as well. So all of us have lots of mutations in different cells in our body. So it's not surprising that even twins are different, but even the NASA scientists were surprised at the level of change. Yeah, come on, you can come on in, it won't bother me. So these changes, these mutations even for twins, and they believe maybe stress, the environmental stress, the space travel may have triggered some of these events that then made them different. One thing I wanted to say too, that's often reported, there was a bunch of stuff in the news like, went up to space and now my twin didn't return or something like that. They're still twins, their still DNA is remarkably similar. Okay, things are. What happened were just some genetic changes things are. But more than, say, the expression, what really seemed to happen and what has scientists interested, what seems to have happened in space is that genes were expressed differently. And this would take way too long to go into, but those of you who have that DNA is essentially turned on, genes are turned on, translated into proteins, and how they're turned on is a big area of study right now, epigenetics, other types of triggers that change gene expression, but something was different in space, whether it was the stress or the environmental changes or whatever, but the human genome has that capacity to alter itself, to change its expression in response to space travel. And that could be potentially good, probably, to adapt to those changes. It also could have some effects that may have to be dealt with, especially upon return to space. So I think, we're very early on. I mean, we're a long ways to say we don't know how long humans can survive in space. We don't know what necessarily the long-term consequences are, but a lot of study going in, and certainly nothing, I would say, I guess, in my opinion anyway, things that we've looked at this point, there's nothing to say that it cannot occur. It just will take some fairly innovative solutions and certainly some close study of the human body to determine whether that occurs. Okay, do we want to, Steve needs to set up, right, for the things are, okay.
So everybody, just and for those of you who just come in, my name's Dr. Maloney, kind of emceeing of things here today. Welcome for those of you who just joining us to Space Day 2018 at Dakota State University. We're going to have Science Steve come up in just a little bit. We have to do a quick AV check with NASA, actually, for the downlink. That'll be at 11:10. So you may see some video and some audio going in, kind of like the Wizard of Oz, pay no attention to the man behind the curtain. That'll just be a couple of minutes, and then we'll get Steve started. A couple of logistics things. So folks in the bleachers, if you're DSU students, come on down front. We're actually going to save that space. We have about 90 8th graders from Madison Middle School coming over, and we're going to keep them put up on the bleachers. So definitely fill in the spaces here. Those of you who are on our list of question askers, you'll notice you have seating along the rows over here with your name on it. So Afternoon here with the rest of our program, and obviously we have more people keep wandering in along the way. I want to start off by introducing Anya Hartman? Hartman. From the U.S. Geological Survey's EROS Center, just about 45 minutes away from here. Phenomenal facility, doing great work here, and again, a lot of DSU students involved in what's going on there, both as interns and graduates. So without further ado, here's Anya.
Thank you. Good afternoon. I'm going to talk to you a little bit about Earth from space. We image the Earth via satellite. Our series of satellites is called the Landsat satellites. And like the ISS, we're in orbit above Earth's surface. The ISS orbits around 250 miles above Earth's surface. We're around 438 miles above Earth's surface. Earlier, we heard that the ISS makes an orbit about every 90 minutes. We orbit every 99 minutes, so about every hour and a half Landsat passes. Again, we're from the U.S.G.S. EROS. And for those of you that don't know, U.S.G.S. stands for United States Geological Survey, and EROS stands for Earth Resources Observation and Science. We speak in acronyms there, and it's entirely possible that I might throw a few acronyms at you. So if I do that, go ahead, flag me down, wave at me, say, hey, Anya, back up, and I will slow down and I will spell out those acronyms. So satellite imagery is our bread and butter. Landsat is sort of how we got incepted. The whole idea of got a clear picture of what the Earth looks like from a distance. All of the artist renditions prior to that, they would show clouds. They wouldn't show any clouds. It was the continents, and that was it. For the first time ever with the Apollo mission, they said, look at what the Earth is doing. What if we send up a satellite? With a satellite, we can tell what is going on with the Earth over time. And here you can see we have satellite imagery from 1985 as well as 2014. There's a big difference, isn't there? This is deforestation in South America. In addition to our vast archive of satellite imagery, we also have aerial photography. We have aerial photography dating back to the 1930s. We have almost the entire country throughout those years. So if you're not from South Dakota, if you're not from Sioux Falls, we would probably have your location as well, including Madison. Anybody recognize that building? You are here. I understand the pointer doesn't work on this, but you are here. Anybody deal with data storage here? A little bit at DSU? I understand there's a lot of people interested in database. We have a very huge film archive, again dating back to the 1930s, and we're making all of that film product digital. That takes a lot of space, doesn't it? This is one of our storage facilities. At EROS, and I'll talk specifically about Landsat quite a bit because that's really our bread and butter, but at EROS we also have a wide variety of science products, including the aerial photography, the satellite imagery. We have topography products, we have land cover products, and a wide variety of other science products. This is one of our storage facilities. We have 80 petabyte capabilities with this. Currently only 12 capacity is used. So I talked a little bit about Landsat's orbit. We are polar orbiting, whereas the ISS is equatorial orbiting. So as the ISS goes like this, Landsat's going like this around the Earth. As we're doing this, the Earth is turning underneath, and that's how we get our different collects. Again, we're 438 miles above Earth's surface, so with that we can get and capture a lot of the Earth as it spins underneath. We have repeat coverage every 16 days with one satellite. We currently have 2 active missions, so with Landsat 7 and Landsat 8, we get repeat coverage every 8 days. These are our earlier satellites. The very first Landsat satellite was launched in 1972. So again, over 40 years of satellite imagery, we can really tell what's going on with the planet. A lot of people will ask me, well, how long does an average satellite last? The earlier satellites were highly experimental. If they lasted 1 year, we were really excited. We typically got about 3 years out of them. The mid-satellites, we expected to get 5 years out of them. And Landsat 5, which is in the lower corner, for Landsat 5, we launched in 1984 and decommissioned it in 2013. So we got over 28 years worth of data from Landsat 5. It's a very good return on investment. Next to it is Landsat 7, launched in 1999, still orbiting, still ingesting data. And our current mission is Landsat 8. Landsat 8 is also still orbiting, still ingesting data. It was launched in 2013. We're currently in development of Landsat 9. Landsat 9 is expected to launch December of 2020. With Landsat 9's launch, Landsat 7 will be deorbited, and Landsat 9 will take its location. Are questions allowed? Typically, I would ask any questions, but I'm not sure how we have time. Yes? Oh, all right. So people will ask, what do you do with the satellite imagery? What can you actually see? Has anybody been following the California fires? That's one thing that we can detect really well. Our satellites are 30-meter resolution imagery, so you're not going to be able to tell what your neighbor is grilling for supper in their backyard. But for scientific purposes, for monitoring what the planet is doing, it really does an exceptional job. And after the fire goes through and is burned out, another thing we can do with this imagery is we can watch regrowth in these locations. I typically do this with my 5th graders, but maybe you'll have some fun doing this too. These are 2 images of southeastern South Dakota. Anybody notice what is going on in these images? Can you tell me what the change is? Yes, there is flooding. And the laser pointer is not going to work, I understand, but in the right-hand image you can see, I believe it's the James River Valley, is increased in size greatly, as well as, I guess that's probably the Sioux River on the further right-hand side. How about this? Yep, that is correct. We have some ice sheets melting, breaking away. How about this one? That is right, Central Pivot Irrigation System. This is a desert in Saudi Arabia. It doesn't look like a desert anymore, does it? This one might be a little trickier. This is urbanization in the Delta River area, Delta River Valley. Quite a bit of growth between the 2 images. This is a lot of what we do with Landsat. We study change over time occurring across the planet. Any questions?
So when, I know that data and images go up on the public website. Is there a delay between when things are, taken or captured by Landsat and when they become available to the public versus maybe researchers who are working at U.S.G.S?
Everybody gets the data at the same time with Landsat. Within about 2 hours after it's acquired, we have it available for download. Yes? Previously, Orbital had done our launches. We're looking at both Orbital as well as SpaceX as a possibility. Yeah. And as that works, a bid goes out, whoever gets the bid gets the launch. So, and I probably should have mentioned this earlier, our satellites are launched out of Vandenberg Air Force Base in California. So we can't really track animals, right? They're too small. But one thing we can do is we can monitor their habitat. And if you notice in this image, we can monitor penguin migration, penguin colonies via the poop on the ice sheets. This is a study that's being done in England. People are like, well, do you think we can do this? Do you think we can study animals from space? Well, it turns out that we can. Penguins tend to leave a nice, large brown smudge across the glaciers in Antarctica. And that is something that we can see. You might not be able to see the penguins, but they leave behind a mess. Here's another image. You can see a brown spot, and so I don't think, yeah, you can't use it. Right in the middle, there's a couple of points that stick out a little bit further. That's where the colony would be. And that wraps up my presentation. Are there any final questions? We have tours at 10 o'clock and 2 o'clock Monday through Friday. We do offer job opportunities, internships, as well as job shadowing, where we can sit you down with a handful of people that would be in your field. And you can sit down with them for 40 minutes to an hour. So if anybody is interested, I'm the right person to contact. My name is Anya, and thank you for listening.
So, thank you, Anya. Really interesting facility. If you have not had a chance to get down there, we went down there with our STEM Institute group just about a week ago. Phenomenal facility and doing a lot of things here with our students at DSU. Next up, I'd like to introduce Peggy Norris. Peggy is the Deputy Director for Education and Outreach at the Sanford Underground Research Laboratory. Sanford Underground Research Laboratory is located in Leeds, South Dakota. It's the old Homestake gold mine. And basically, a mile underground, there's all sorts of science and experiments being done there, many of them through Black Hills State and School of Mines. We also have Dr. Gaylor who's participated in some research deep underground there, where it's shielded from cosmic rays. We have a slightly different environment, and it provides us with some great opportunities. The facility will also be hosting the FAR detector for the DUNE experiment, the Deep Underground Neutrino experiment, in the coming years, and Dakota State is involved in that. I'm the PI here for our...
Brochures about it on the table.
Yep.
I'm not going to talk about it,
But, yep, for people who are interested, we're involved in that. I've been doing some work related to the beam that will be coming from Fermilab deep underground to South Dakota here. And definitely we can talk about that in the coming years as things ramp up. Without further ado, Peggy Norris.
Do I need to use the microphone for the video?
There is also a handheld one as well.
Because I think...
If you want to use that.
Yeah, if I need... Hello? Okay. All right. I like to walk while I talk, so I'm not going to stand back there. So what I'd like to talk to you about today is some work I've been doing that's NASA funded the last couple of years, since, well, actually for quite a bit of time during my career. So I'm not going to talk so much about Sanford Lab, just very briefly, but I think we agreed that I'll come back sometime and give a talk on Sanford Lab itself. But I am in the Education and Outreach Department at the lab, and besides the work I do with K-12, I also run the internship program, and we have the Davis Bacall Scholars Program and other opportunities for undergraduates. So if you're interested in paid internships in the summer, keep an eye out. I'm also on the management team for the South Dakota Space Grant Consortium, and they give out about approximately $160,000 a year in fellowships to primarily undergraduates across the state. So usually we put out the announcement in November. You can apply for basically educational stipends, which range from $1,000 to $2,500 a year, or you can apply for a research stipend or a NASA internship. So those will come out in approximately November, and then we make the decision in the spring for the following school year. So those are available to students at all levels, undergraduate and graduate. So if you have any questions about those kind of opportunities, you could contact me later. But for right now, I'm going to talk about space radiation, primarily cosmic rays. But what is space radiation? Well, it's one thing it is a major hazard for future space ventures. Astronaut Arnold mentioned that at the space station 200 miles up, he's still within the magnetic field of the Earth, so he's protected from a lot of space radiation there. But in order to go to Mars, it's going to be a bigger issue. And so here is some of the problems are both biological because radiation will do damage to DNA, and it also does damage to electronics. So they've got to solve the issues in both sides of things before they can really safely send people on distant missions. There's all kinds of things that are considered space radiation, and anything from meteor debris up to high-energy cosmic rays. And I'm going to talk about the latter because that's what I've been doing research on over the years, and we've only got a few minutes. So what are the sources of cosmic rays? So first of all, who can tell me what the most abundant element in the solar system is? Yeah, hydrogen, by a long shot. And most of the hydrogen that bombards us comes from the sun. So this is, on this side is the wind, the solar wind hitting this octopus-looking thing are the magnetic field lines of the Earth. So the Earth's that little thing in the center of that. So the solar wind is streaming out, and the Earth's magnetic field protects us from that. But radiation gathers in belts called the Van Allen belts, and most of it is hydrogen, but there's a fair amount of radiation that goes as heavy as iron, and occasionally even heavier, and those collect in the innermost belt because of their charge and the magnetic field. And those can be a real issue for satellites and for electronics in those satellites. So the first thing I'm going to talk about from one perspective is using accelerators to tell whether your satellites are going to survive space. And I'm sure Landsat was designed with this in mind too. This is a facility I helped build at Lawrence Berkeley National Lab in my time out there. And this is a proton on the screen there is our proton irradiation facility. So looking at hydrogen, NASA, aerospace industries, and Defense Department, they would all bring parts out that they wanted to put into spacecraft and test them to see if they were going to survive space. Because you don't want to build a $2 million or whatever satellite, send it up, and then find out that your electronics is going to fail. So you have to test everything. So we did a lot of this testing. And not only with protons, we tested with things as heavy as uranium, because protons are very, very abundant, but they don't leave much energy as they go through material, whereas something like iron leaves a lot more energy and can do a lot more damage. So we also used this facility for biology. We tested cells, saw how the DNA fragmented and repaired itself. So we were able to try to come up with ways to make space radiation less of a hazard for future astronauts and so forth. Okay. Well, those cosmic rays that are in space and an issue for space travel do hit our atmosphere. Some of them do get through the magnetic field. And when they do, they make a shower of other particles. And what we can see on the surface are muons. They're like a heavy electron. So that's the mu sign down there you see coming down. And if you had a detector, like what these students are holding, made with plastic scintillators, very simple detector can detect those cosmic ray muons. And you'll see a few a second, so maybe 10 a second on the surface. So in something the size of your hand, you'd get about 1 a second, okay? But that, for the big science experiments we're planning to put underground, is way too much background, because these very, very large, imagine a detector the size of a football field and 7 stories tall. tall. That's the kind of thing they're going to build for Dune. If you had that on the surface, it would be seeing millions of cosmic rays a second, and you would not be able to see the very rare events that they're trying to look for. So something like dark matter, they may see one a year. So you can't do those experiments on the surface. So that's why we go a mile underground at the lab. So here we are out in Lead, and here's a cross-section of the lab at the 4850 level where most of the science is going to happen. A cosmic ray would go through your hand about once every 3 months. So it cuts down the cosmic rays by a factor of 1,000,000. And this little animation was done by Dakota State for us many years ago, and we still use it to kind of just show when we go into classes that the rock is going to get rid of almost all the cosmic rays. So there's the head frames of Sanford Lab. These are our shafts, and there's the experiment down there, and all the cosmic rays go away, or almost all of them. So the first person who figured out you could go underground to get away from cosmic rays and look for very rare events was Ray Davis, and he built this tank with 100,000 gallons of dry cleaning fluid and won the Nobel Prize for that in 2002. He ran that experiment starting in 1965 for about 30 years to try to understand what's happening in the core of the sun by studying neutrinos. What they learned was that we didn't understand neutrinos, and that's led to the Dune experiment and much other work since. So that's all I'm going to really say about the lab, except here is the map of the 4850 level. And we have several experiments running now, searching for dark matter, trying to understand some properties of neutrinos, trying to understand the kind of nuclear reactions that happen in stars. And in the future, the green up there is the Dune experiment that's going to be, they're going to start construction over the next year or two. And the experiment's going to be finished in about 2025. Okay, so some of our undergraduates have worked with me to build some cosmic ray detectors that are big enough to actually see maybe 3 to 5 cosmic rays a day. So we have those underground, and we're trying to really calibrate whether we can see cosmic rays underground. So that's kind of one project we've worked on. And now, very quickly, I want to mention 2 other projects. And let's see. The Eclipse project we did last year was a big national project. Did you guys see the eclipse here? It wasn't total, I know, but was it cloudy? Ah, well, if you're in a balloon at 80,000 feet, you're above the clouds. But we were in western Nebraska. So what NASA decided to fund was university groups from all across the country to film the shadow of the moon coming across during the eclipse. So we weren't looking up at the eclipse. It doesn't really make much difference whether you're on the surface or whether you're at 80,000 feet, except for the clouds. But we were looking down at watching the shadow come across. And the tricky part of this project was they wanted every one of these 55 teams to live stream to NASA TV as it came across. So the idea was that the first team was going to be off the coast of Oregon, and then as the shadow came across in whatever, I forget how long it took to go across the country, something like an hour and a half, I think, everybody got their turn on NASA TV. Our team was the only team in western Nebraska, so we had like our 3 minutes we were supposed to be broadcasting. Well, that was the one thing that didn't work. So unfortunately, this was a very interesting project because we were all working as teams, but we were all integrating software and everything else. And the Montana State Space Grant led the whole thing. And they sent out a software update like 3 days before the eclipse. And we had already done our final testing, our final launches. Everything was working perfectly. And then on the day of the eclipse, we launched from Scottsbluff, Nebraska. It was about 90 miles from Alliance, which was on Centerline. And the idea was you time everything perfectly, your balloon's going to be at 80,000 feet looking down right at totality. So you have like a 2.5-minute window. This was tough in ballooning, but we managed to make that work. The only thing that didn't work was that the modem we had on the balloon didn't link properly to the modem on the ground in Alliance, and that would send it to NASA TV. But we got beautiful footage, which I'm going to show you in a minute. And but I think I'm going to come back to it, make sure we have time. I want to tell you about our new experiment first, and then I'll come back and finish with the video of our eclipse. So the idea was to take this high definition video, but also to live stream some lower definition video. And we also had a cosmic ray detector that measured gamma rays, so secondary radiation, not those primary protons. We also measured a biology sample for a NASA group, and we ran a payload for another university that was measuring some atmospheric data. So we did all that, and this was the team on launch day, and I'll come back to the video, launching from a farm near Scottsbluff. And all that worked. We had problems with crowds and trying to get to our payload when we were done and all of that. But since I don't have much time, I just want to tell you where I'm going from here. I'm getting on a plane this afternoon and heading to New Mexico on a project called H.A.S.P, which stands for High Altitude Student Platform. So our balloon team went on and put in a proposal to NASA, and they launched a very large balloon. You can see it up in the upper part there. That I think we're going to hear from Raven Industries next, but it's zero pressure, so it'll stay. Our weather balloon that we launched in Alliance just went up, then it popped, and it came down. So it was only at altitude for a couple of minutes, whereas this one's going to be up for like 16 hours. So they're able to control the pressure of the helium to keep it. And it goes to a higher altitude. So we're launching from this place called Fort Sumner, Nebraska this weekend. So we're heading down there. We'll be down there starting tomorrow, integrating our payload into their system. And I wanted to measure primary cosmic ray protons, because we're going to be high enough for long enough to do that. Well, I have a little tiny detector in that black part on the front of this thing. In a laboratory, I would use a whole nimbin of electronics to pull a signal off of that detector, digitize it, amplify it, and get it to a computer. All that has to be on this one small board. You can see the small screwdriver that shows you the... So our computer is a Raspberry Pi. And we have little tiny preamp board, amplifier boards, and NASA gives us 30 volts, 15-watt battery. Everything has to run, so we have to actually boost that in order to put 200 volts on our silicon detector, plus bias all these boards and so forth. So it's really tricky. I don't know for sure it's going to work. I just ordered a new board overnight because we seem to have fried one in the laboratory this weekend. It's getting delivered to my hotel on Tuesday, so I'll let you guys know how it went after the fact. Yes, we are crossing a lot of fingers. So we've had a lot of students that have worked on these projects, and I haven't tried to name them all. We had 2 senior design teams at School of Mines over the 2 years, one for the Eclipse project and one this past year for the H.A.S.P project. Plus, we've had interns working over the summers, both high school and college, and high school students. And the funding has come from the NASA Science Mission Directorate, the Balloon Project Offices, and the National Space Grant. And now, I'll answer questions, but I just want to get to this video first, so you can watch it while you ask. See if this will work. No. Do I need to control click? Well, let's see. Let's just do this. Sorry, I didn't get a chance. I should have been doing that instead of drinking coffee before we started. Talks back up. I don't know we want to wait for updates, do we? Do we? All right. Do you guys have questions? There we go. This is a video that one of the students put together. So, let me just turn down the music. So that's the shadow of the moon as it starts to
And so next up, we have a speaker coming in from Raven Industries. Going to talk a little bit about some of the work they do at Raven Aerostar. Brian Matherly.